and we'd like to show that U must be open. So if we pick Z as a point in U, we'd like to show that there's a neighborhood of Z, which is again in U. That would show that U is open. So if Z is not equal to 1, then Z is equal to omega of S naught for some particular S naught in that. And that means we can find an epsilon such that, plus or minus epsilon from S naught, that's in this inverse image of U. Great, so that's the neighborhood. On the other hand, if Z is equal to 1, then both 0 and 1 are in the inverse image of Z. So that means there's some epsilon naught. We end up having to take like this part and that part union to form the neighborhood. But that's fine, because in either case, it follows that U contains a set of the form S1 intersect W, where W is an open wedge in polar coordinates. And the wedges in polar coordinates are open subsets of the plane. And remember, the open sets on the circle are defined by the intersection of open sets in the plane with the circle, which makes it open. So lo and behold, it's open. And since that then shows that omega is a quotient map, he says, on the other hand, if we restrict it to 0, 1, it's still surjective and continuous. So this was, so this is omega from 0, 1, both, that is from 0 to 1 inclusive, right? Now here he's thrown out the 1, and that spoils it, because if you do that, then you have, it's surjective and continuous, but it's not a quotient map, because if you look at 0, 1/2, it's a saturated open subset of 0, 1, but the image is not open in S1. So the reason this is not open in S1 is it's like, it would give you a subset of the circle, right? That's got it's got a filled in point 1, and then it goes over and it gives you an open other side, right? That's not an open subset of the circle. So anyway, moving on here. If we have a surjective continuous map that's also an open or closed map, it's a quotient map. This is, as he says up here, it's sufficient but not necessary. But if we have a surjective continuous map that's either an open or a closed map, it's a quotient map. That's great. And a nice application for that is if you've got the Cartesian product of k topological spaces and you just look at the canonical projection onto the ith one, well, that's a quotient map because this is an open map. And since it's open, that's a quotient map. And then he draws the thoughts together here just to give you kind of a nice big picture of everything that was just said. If you have x and y topological spaces and F is a continuous map that's either open or closed, then if F is injective, it's a topological embedding. If F is surjective, it's a quotient map. If F is bijective, it's a homeomorphism. So topological embedding means something like the image under F is itself a topological space, something like that. I'm a little rusty on the precise business there. Now this right here is an example of, I would say, category theoretic type thinking. I mean, this is next level of mathematics. It's the use of what's called the universal property. So, well, characteristic property here, but if you have x and y are topological spaces and Q is a quotient map, all right, then for any topological space Z, this mapping is continuous if and only if the composite map F composed with Q is continuous. So that's kind of interesting, right? Because like Z is any topological space. It's saying you can probe the continuity of a mapping from the quotient space to Z in terms of, how it behaves under composition with the quotient map from the space which is quotient. That's an interesting result. And what's perhaps more interesting is this one, which is that if you have a given topological space X and a surjective map Q from X to Y, the quotient topology is the only topology on Y for which the characteristic property holds. All right. And then beyond that, we have this passing to the quotient theorem, which says if Q is going from X to Y as a quotient map and Z is a topological space, f going from x to y is any continuous map, constant on the fibers of Q, all right? Then there exists a unique continuous map f tilde from y to z such that f is equal to the composite of f tilde with Q. So this is called passing to the quotient. We can take a mapping defined from x to f, from x to z, right? And provided this f behaves well with the quotienting process, right? F has to be constant on the fibers, which you're squishing to make up the y space, basically, right? If that's the case, then you can pass to the quotient and define this f tilde like such. So it's quite cool. And the proof is pretty simple, right? Like the existence and uniqueness of f tilde follows from elementary set theory. Given y and y, there is some x and x such that q of x equals to y, because it's a surjection, right? We can set f tilde of y equals to f of x for any such x. Then the hypothesis of f guarantees that f tilde is unique, right? Because we know that f is equal on fibers, right? So it doesn't matter which y I pick, you know? Excuse me, which x I pick. They all map to the same y under Q, you know? So that means that f tilde is unique and well-defined, and then continuity of f tilde is immediate from the characteristic property because, well, we have to go back and understand the characteristic property, but there it is. But this is actually not the part which is most interesting, I think. The application of these theorems is actually quite striking. So I want to get to those, okay? So like, so in the previous theorem, we say f passes to the quotient or descends to the quotient. So the formula for f tilde is f tilde of the quotient map equals to f of x. All right, great. Or in terms of the equivalence class notation, if the quotient is mapping to the equivalence class, you know, for a quotient which is defined in terms of an equivalence relation, this is how f tilde works. All right, great. So if S is the quotient space of R determined by the equivalence of example 350, which was that two real numbers are equivalent if they differ by an integer. That was the equivalence relation, all right? If we have f going from R to x is a continuous one periodic map, meaning that f of x is equal to f of x plus 1. If that's the case, you can easily prove by induction that f is equal on you know, a whole grid of numbers which differ by just integers, right? Like a x plus z would be the set. You know, f of x plus z is equal to f of x, is what I would say. So that means then that we can see that f descends to a continuous map f tilde from s to x because it's equal on the things we're forming the equivalence here. Okay, so this one actually, the way this is applied and the page after is really, really cool. If you have two quotient spaces, all right, Q1 goes from x to y1 and Q2 goes from same x to y2, and they're quotient maps that make the same identifications. In other words, Q1 of x is equal to Q1 of x prime if and only if Q2 of x is equal to Q2 of x prime. All right, so they're making the same identifications in the quotient. Then there is a unique homeomorphism phi from y1 to y2 such that we can relate that homeomorphism in the quotient maps in this way. So phi composed of the first quotient map is equal to the second quotient map. So the proof is given here, and I think the proof is not that hard to understand. I'll let you guys look at it, but check this out. So to show that the quotient map, quotient space I mod tilde of example 3.47 is homeomorphic to the circle. So let's, oh man.
It's probably 1 equals 0.
Yeah, that is probably the 1 equals 0. Yeah, we're taking I and we're squishing it, right? So you're right, that's exactly that one. It was the 1 equals 0 equivalence. Everything else remains unidentified, you know. everything else is just identified to itself.
347
right?
was 1 equals 0.
Yeah, okay, so to show that that's homeomorphic to the circle, we just need to exhibit a quotient map, omega, which also has I going to S1, and it has to make the same identifications as tilde. But that's exactly that long example I just bullied you through about 10 minutes ago with the omega and the S naught and the plus or minus epsilon business, all that. That is a quotient map from I to S1, where you're making the same identifications in I as is done in 3.47. Therefore, it means that this quotient space is homeomorphic to the circle. So now that's how it's proved. I mean, there are other ways, but that is a way. So these adjunction spaces are pretty neat. The idea here is if you have F, a mapping from A to X, right, a continuous map, what's essentially done is that you are using the map F to glue A to where it goes to. So like you're gluing A to its image, and then so like X, the disjoint union of X and Y is this big space, right? And in that big space, you're connecting A and its image under F as one point. So like this, as a special case, if your function only was defined on the singleton mapping to another singleton, like if you had a really stupid function, it just maps f of x to y, then this would be the wedge sum. You're just gluing space x and space y, putting x and y together with your function f of x equal to y. That's one application of this adjunction space. And F is called the attaching map. But of course you could do more than that, right? And they have really cool properties. Which I'm going to skip over here. The examples, though, I think are interesting. Like I just said, the one example would just be the wedge sum, which is for like a really dumb function, right? A is just a singleton. The wedge sum is a particular example of this adjunction construction. If we let A be the circle, subset of the closed disk, and we look at the inclusion map, then the adjunction space is homeomorphic to S2. You can check using the techniques of the previous section, all right. But what's up next is actually really, really interesting. He talks about M and N manifolds, all right. Then they have boundaries, boundary M, boundary N. If they're both n-dimensional manifolds and they have homeomorphic boundaries, and you have a homeomorphism that goes from the boundary of n to the boundary of m, then you can use the adjunction construction on that homeomorphism of the boundaries to glue these two manifolds together by this construction. You just take the boundary of manifold M and the boundary of manifold N and stick them together. Chunk. And then you've got a bigger manifold that's got M on the one side and N on the other side, and they're glued together at the boundary. What would the boundary of such a manifold be? If you glue the boundary of M to the boundary of N, what's the boundary of the adjunction, the space you're forming from this gluing? Dr. Schmidt has an idea. I can see it. That's a good question. No. So that's it. Is if you glue the boundary to the boundary, it's no longer a boundary. It's just part of the interior of the adjunction space. So that's the trick. And the thing is, if you take any closed manifold, if you take any manifold with boundary, right? Is the boundary of that manifold homeomorphic to itself? It is. You just take the identity map, right? So if you take a closed manifold, a manifold with boundary, and you glue the boundary, take another copy of it, right? Take the disjoint union of your two manifolds and then identify the boundaries of each, then you've got an open, a boundaryless manifold, a manifold without boundary. which is, you know, it's called, I believe this is called the double of the manifold. Now, to prove that, you have to actually sort through how the boundary charts work together for good and such. There's about 2 pages of boundary chart finagling, which is not the point of this course here. But yeah, you can do that. So I think that's kind of neat. That's called the double of a manifold. Right. So if you know that, then you can say this: every n manifold with boundary is homeomorphic to a closed subset of an n manifold without boundary. So then the rest of this, I don't think I scanned the rest of this chapter, but man, I'd like to talk to you guys about some of this stuff, but I probably shouldn't. But well, I'll think about whether or not I should misbehave and tell you more about topological groups next time. I should do it. I skipped ahead a bit in the book. This is like 30 pages later, after he's discussed compactness and connectedness and some other things that I won't do because Dr. Sprano has already talked to you about that in your topology course. So this is the so-called closed map lemma. Suppose F is a continuous map from a compact space to a Hausdorff space. F is a closed map, which means it maps closed sets to closed sets. That's what that means, right? If F is surjective, it's a quotient map. All right. If F is injective, it's a topological embedding. If F is bijective, it's a homeomorphism. So what's the precondition here? It's just that F is a continuous map from a compact space to a Hausdorff space. What's a compact space? Well, that's a question for topology, isn't it? So, but if you want me to give you a brief definition, I mean, the technical definition is that every open cover has a finite subcover, is the topological definition of compactness. My brother says if a space is compact, it has a certain finiteness. Kind of it's a way of capturing a certain finiteness about a space. But anyway, that's for another day. The applications of this closed map lemma are really pretty cool. It completes the story of the examples I've shared with you guys. That's why I wanted to do this. We showed that the circle is homeomorphic to a quotient of the units or interval, right? The tedious part of that proof was the example 3.66 with the epsilons and such, showing that the map omega from the unit interval to the S1 is a quotient map. Now, we can simply say that omega is a quotient map by the closed map lemma. Because I is a compact set, and S1 is Hausdorff. So by the closed map lemma, this is a what? So we have a surjection from, it's a surjection, right? Let's go back up to the thing again. Continuous map from a compact space to a Hausdorff space. The circle is a Hausdorff space. You can separate any 2 points on the circle with open neighborhoods, if you know, of the circle, if those 2 points are disjoint. And the unit interval is compact, so if F is surjective, it's a quotient map. But omega was surjective, so it's a quotient map. I think that's, you know, if I was taking this as a graduate class, I would make sure I knew this closed map lemma before I took my final. Because I would much rather be proving something is a quotient map with this lemma as opposed to the way I was showing you 15 minutes ago. You know, that's nice. Another example, if we have the quotient space of the square I cross I pasting the boundary side segments together, top and bottom, right? I claimed it's homeomorphic to the torus. Here's proof. Construct another map from the Cartesian product of the torus to T2, setting using just basically it's the omega map times 2. See, e to the 2 pi u, e to the 2 pi iv, right? Well, guess what? This is compact because you know, the Cartesian product of the compact sets is compact here. And
Do you have information
Oh, you're fine. Cool. So this is compact, and the torus is Hausdorff. If you take 2 points on the torus, you can separate them using, open sets. In fact, this is Hausdorff. As such, this is a quotient map. All right? So, and it makes the same identifications on I cross I as was made in the pictorial thing where I was saying this goes this way, this goes that, this is with this and this is with that, right? The same identifications are made on the Cartesian product of the interval itself. Therefore, that means that there's a homeomorphism from the torus to the identification space that we introduced in the first day. And that's the proof that that gluing space, where you take the page and glue it to itself and itself again, that I can't actually do with a physical piece of paper, I need a rubber sheet or something, is actually a torus, topologically speaking. These arguments are just so much nicer than the ones I gave you earlier. In proposition 3.36, we used an explicit computation to show the donut surface is homeomorphic to the torus. Now that the proposition can be proved much more simply, well, anyway, I don't know if we actually did that. So that's kind of that's part. I don't think that's even part I gave it to you guys. This one's nice. Projective space Pn is a quotient. We defined projection space Pn as a quotient of Rn minus 1, 0. Remember, we identified our identification space. We're not just rays, but actually lines with the origin deleted. For that was the equivalence there. And he says, well, that can be represented as the quotient of the sphere with antipodal points identified. Let squiggle denote the equivalence relation identifying antipodal points, the antipodal equivalence. Then S mod the antipodal equivalence is homeomorphic to Pn. To see this, let Pn go from Sn to Sn mod the antipodal equivalence denote the quotient map, and just consider the composite map. Include Sn and Rn plus 1 without 0, and then the quotient map from there to Pn, where I is inclusion, and Q is a quotient map. Note that Q composed with the inclusion is a quotient map by the closed map lemma. Why is that? What do you know about Sn? This is compact. And this is Hausdorff. So this is a quotient map by the closed map lemma. And it also makes exactly the same identifications as P. Like this quotient map makes the same identifications as did our previous one. So that means that Pn must be homeomorphic to Sn mod the antipodal equivalence. So when you start working with projective space, this antipodal equivalence, you'll appreciate that it's just there. You see it as soon as you start working with these things. Like you just. Oh, finally. This one here, the closed N disk, I guess, mod the n-1 obtained by collapsing the boundary of this to a point. We claim that is homeomorphic to Sn. We just need to construct a surjective continuous map from the closed disk to Sn, which makes the same identifications, and such a map is automatically a quotient map by the closed map lemma. So this is the map. This Q of x, well, I'd have to work on this for a minute to understand it, but maybe that should be a homework problem, is to explain example 4.55. I don't think it's that hard. I just think our time is up. So, so here, oh my goodness, yes. Sorry guys. In example 3.53, we had the cone, right? Now we can show that the cone of Sn is homeomorphic to B bar n plus 1. What did it say before?
Yeah, that is a cone Sn
Sn is homeomorphic to, see here, example 3.53. CSN is homeomorphic to Bn. All right, what does it say in the later one? So remember that. CSN, let me just write it down. I'm going to write it down. CSN homeomorphic to Bn. Example 4.56, he's saying CSN is homeomorphic to Bn plus 1 bar. Remember, we said, no, we don't believe this, typo. Vindication. So here's how to show that. The continuous map f from Sn across the identity map is, you can just define it to be, so all you do, this is a really cool map actually. So you take the direction from Sn and then you just scale it by the number over here. So as the S ranges from 0 to 1, you go from the origin out to the point on the n sphere, and you fill out the whole thing. But that's the closed ball, you know. So this fills out the sphere, whatever this thing's called, the b bar n plus 1. And it's a beautiful map, but that's a quotient map by the closed map lemma because this is compact and that's Hausdorff. So yay! And so it maps this set to 0 in there, and it's injective elsewhere. So it makes exactly the same identifications as the quotient map we looked at, the cone quotient map, and therefore the cone over Sn is homeomorphic to the bn plus 1 closed set there. The closed n plus 1, I don't know what, I need to come up with a name for the stupid thing. I mean, it's just the solid sphere of dimension n plus 1, I think. Like B2 bar, I believe, is just the closed disk of radius, unit closed disk. So anyway, mastering quotient spaces is no small order. We all have lots to learn, like me included. But I just wanted to give you guys, a good introduction to it. This last thing here, if we have a compact Hausdorff space, Q is a quotient map, the following are equivalent. Y is Hausdorff, Q is a closed map, this set is closed in X cross X. I wanted to get, there's something else I wanted to say today. Yeah. Rats. Well, anyway, one of the things I wanted to mention was the wedge sum we looked at early towards the start of class of like H3, the zero divisors of H3. That is not a manifold. Neither is the wedge sum of the lines or the circles, because they've got these points that aren't in one-to-one correspondence with an open set of Euclidean space. Like so a manifold has like the same dimension everywhere. It's like you have to have one-to-one correspondence with open sets of Euclidean space of a particular dimension for the manifold. Like I can't have parts of the manifold be two-dimensional and our other parts be three-dimensional. That's not allowed. All right?
What about the boundary?
Even the boundary of a two-dimensional manifold is two-dimensional. So like, because the open subsets of the boundary are just, they're, I mean, so if this is my manifold, right? So you've got these kind of open sets up here, right? But on the boundary, so I'm drawing the bottom edge as if it's the boundary, okay? Those are still, like down here, this is not the chart on the manifold, this is still part of this. Right, and so that's this and that. They're still in, you know, bijective correspondence with some subset of like the plane. No. Right, that point ruins it. Like you can't get a bijective correspondence between like the line or this one here. You know, what would you do? It's two-dimensional on the plane part. It's one-dimensional on the line part. It's not a manifold, you know? So, I don't know. I think these are interesting examples of non-manifolds. Anyway, I should shut up for today. Hopefully tomorrow, listen to me, Thursday, we should start talking about homotopy. And I should hopefully have the homework for this part of it for you guys, like soon. So, I would like to start grading previous homeworks.